Good evening. Can you guys hear me out there? Let's go ahead and find our seats. I want to try to get us started as soon as possible. I know we had a rather large session just a few minutes ago and folks are still clearing out. Hopefully you're all here for the Wright Brothers lectureship. I'm just going to give it a couple more minutes for people to finish coming in and settle down. Okay, good evening everyone, and welcome to the Wright Brothers Lectureship in Aeronautics. We're happy that you could join us. I'm Fay Collier, Aviation Forum's General Chair, and this lecture commemorates the first powered flights made by Orville and Wilbur Wright at Kitty Hawk, North Carolina, back in 1903. It's one of the most prestigious awards given by the Institute and emphasizes significant advancements in aeronautics and recognizing major leaders and their contributions. We will begin in just a few minutes, but I have the honor and the pleasure of introducing our distinguished lecturer, Hannes Ross, and some background on the lecture itself. Mr. Ross received his MS in Aeronautical Engineering from the Technical University in Berlin in 1964. He worked with Northrop on the VSTOL tactical fighter study, McAir McDonnell Douglas with the F-111 crew escape module, and 3 years on the F-15 conceptual design as in the definition phase as a group engineer. Mr. Ross was the program manager of the German component of the X-31 program. From 1991 to 2001, he was the Vice President of Advanced Design and Technology, Military Aircraft Division, what's now known as EADS. It was DASA at the time. In 2001, he retired, right? Believe that? And he's been consulting ever since. Specifically, Mr. Ross has been involved as a design advisor and consultant for the Solar Impulse Core team since 2004. They are located in Switzerland, and as well, Mr. Ross has a pilot license, or several licenses, sailplane, PPL, ultralights. He is a fellow of the Royal Aeronautical Society, an associate fellow of the AIAA, and a member of DGLR. And he, turns out, plays the accordion. So this lecture is Around the World with Solar Power, an overview about the Solar Impulse program. The Solar Impulse 2 aircraft became the first to complete an around-the-world flight powered purely by solar energy. Solar Impulse 2's record-setting circumnavigation of the world began on March 9th, 2015, departing Abu Dhabi and making stops in 16 cities in 8 nations. Returned to Abu Dhabi on July 26, 2016. During the flight, Solar Impulse 2 flew across the Pacific Ocean for 5 days and 5 nights, from Nagoya, Japan, to Hawaii on the island of Oahu. That leg of the flight made Solar Impulse 2 the first plane to fly across an ocean during day and night conditions using solar energy as its only propulsion system. The plane later flew across the Atlantic Ocean from New York City to Seville, Spain, and in all, Solar Impulse 2 flew 22,915 nautical miles during its 6-month-long flight. It established world records for the longest solar-powered flight by both time and distance. I'd now like to invite Anis to the podium to speak on Around the World with Solar Power, an overview about the Solar Impulse program. Over to you, sir.
Well, ladies and gentlemen, I don't know whether there's anything left after that introduction. So I'll try to emphasize some things that he has not mentioned. And maybe looking back is always a good thing to do, to learn what other people have been done before. And here is a couple, Ferdinand Magellan and Juan Sebastian Elcano, who sailed around the world with solar power, because the solar power generated the wind. And that was 500 years ago. And that's, I think, rather interesting. It took them a little bit longer, 3 years, but it's certainly a big accomplishment. Now, here we have some other airborne first, which I think were also worth mentioning. And very interesting to me, the United States Army with their Air Force, Air Service, were the first to go around the world. Then we had the first airship in 1929. We had a first seaplane. We had a British woman, Ricarda Morrow Tate, and she did that in 1949. We had the first non-stop, no refueling by Dick Rutan and Jana Yeager, as you all know. And the fastest one, I didn't know that either, was with the Concorde in 39 hours. And 31 hours. That was, I think, also a very interesting achievement. They took out everything and loaded all the fuel on there and a few passengers to do it. And then came Bertrand Piccard and Brian Jones, an Englishman, with the first balloon ride around the Earth. And then, 2016, we finished with the first solar-powered aircraft. Now, there's this very famous Swiss family, Piccard. The grandpa developed a nice capsule to go up into the atmosphere, 23,000 meters, so 23 kilometers. You will hear some more metric numbers today, so that may be a challenge. So will be some bloody German accent. But that's what you have to face. So then his son, Jacques, he developed the bathyscaphe, and there you can go down in the depths of the ocean. He sold it to the US Navy, and the US Navy made a smart move. I think they said, okay, we want to go down in the Pacific Ocean. Please come along, because you are the one who knows the system best. He did so, and they came down in the Marianengraben and almost 12,000 meters. That is certainly an achievement. And then the third generation, Bertrand Piccard, did his flight around with a balloon, which was also quite an achievement. And when he did that and landed, it was a hot air balloon. He had about 1% of the fuel left. And he was scared, because if that had happened before, either on the Atlantic or somewhere in the middle of the desert, they might have been in big trouble. they also had on the balloon a solar panel, which gave them enough current and energy to actually operate all their system, from communication, navigation system, and electrical systems on board. And he got the idea that it might be possible to use solar power, fly around the world, and not worry about any power along the line. Of course, he needed, because he is a physiotherapist, he has a leather chair where you can stretch out and tell him everything you have a problem with. But he's not an aircraft designer nor a balloon designer, but he's an entrepreneur, so he had that idea, and he fortunately found another fellow, Andre Borschberg, and he convinced him to actually go along, and they shared the work in the following way. Bertrand would open the doors to the sponsors and to the money chests, and Andre would care and do the program management of the team that is to build the aircraft. Now, initially, not knowing too much about aircraft, they thought that, well, we'll do a feasibility study, see whether it's possible at all, and then we'll build the aircraft if it looks like it's feasible and go around. Now, after the feasibility study, there were some more thoughts from the engineering side, and the engineers did suggest that maybe we build a demonstrator and see whether we can survive one day and one night. If we can do that, then we can continue day after day. And that became the approach, to build a demonstrator aircraft first, see whether a 24-hour cycle can be managed, and then a record aircraft was to be built. Now, the result of the feasibility study in 2003 came out with a recommendation that with a wingspan of about 50 meters, such an aircraft could fly for about 2 days and 1 night, so a extended solar mission, because nobody had done that before. And with a 70-meter, such an aircraft could fly 4 days and 3 nights, based on the technologies available at that time. So since the result of this feasibility study was positive, the initial approach was, let's build a small project team. They would define the objectives and the specifications. Then we'll outsource it. Now, remember 2004, everybody was outsourcing everything, and outsourcing in particular the risk. And that was the idea. When you talk to somebody to pick up that kind of a work package to develop such an aircraft, they would just turn around and leave the place and say, no, we won't do it. None of the biggies like Boeing, Airbus was really interested in that kind, so we have had to review the approach, and the reality became that we had to establish in-house capability in the primary targets and areas like marketing and communication. Somebody had to pay for it. A conceptual aircraft design, fabrication, and testing. And then not to forget the operation of such a complex aircraft worldwide, the flights, the logistic, air traffic control, political aspects, and that decision to go with an in-house capability became the birth of the startup company Solar Impulse. Now, a few basics for such a vehicle. On the left-hand side, you see a little diagram which tells you how much watt hours, how much watt you can collect on 1 square meter. In the summertime, which is the upper curve, and the lower side in the winter. So it immediately suggests that there are a couple of parameters that you have to watch and carefully balance. It's first of all, where do you want to fly? The time of the year, certainly not in winter. The time of the day, if you just want to fly during sunshine. Altitude, you want to fly, clouds, humidity. Cell temperature plays a role because the cell temperature, the colder it is, the better is the efficiency. And of course the cell orientation, it should be right against the sun. Now that, not all of that can be realized, but if you look of how much energy you can collect during, let's say, a 12-hour period during the day, then here comes the question, how do I survive the night? So you have to spread the energy that you collect during the day over 24 hours. And the average solar power, let's say, a typical value here, something like 260 watt per square meter. But you have to look at all the components of the powertrain. So you have to look at the solar cells, what's the efficiency of the solar cells, and there's where the biggest loss is right there. You have to make sure that you can save the energy in batteries. So charging the batteries will have losses. Taking the energy back out will result in losses. You have to have a converter to convert the DC current to AC current, and you have to have a motor and of course a propeller. And along that line, you lose about 85% of the incoming rays from the sun. So that is a relatively small energy which remains. And what you could do, and the yellow equation there, which is derived from the well-known power equals drag times velocity, and drag and velocity, you can see what the minimum wing loading is going to be for a certain power loading that you can have, that you can collect from the sun. And it's much easier to understand if you look at this kind of a plot. You see the wing loading that results from that equation for a given solar power, the kilowatt or watts per square meter. And since you not only have to fly the aircraft, you also have to have communications, you have to have navigation, all kinds of other electronic and electric equipment, you have to subtract that as well. And you see the green area is where you can find a solution, and of course the aerodynamic performance of the vehicle plays a big role. And you see that it varies by the lift to drag ratio, characterizing the cleanness and the aerodynamic performance of that vehicle. Now, you not only have to fly the aircraft and go up there and stay up, but you have to have a mission. And the mission that we flew and designed to is described here. When the sun is starting to rise, you can slowly get off the battery. And if the sun is high enough, you can start flying with solar power. If the sun goes up higher, you fly. You can not only fly, you can start to climb and eventually charge the battery. Saving the energy, you have two options. One is the battery. They are heavy. very heavy as a matter of fact, and you can go and climb up to altitude and store energy in, as potential energy. So we want to be up at maximum altitude at sunset, then reduce the power and glide down like a sailplane. And once you have arrived at minimum altitude, depending whether you are over land or over the sea, you draw from the battery and hope that the battery has enough energy to see the sun come up again. And then the cycle is going to be repeated. So the design objective is that you must achieve a careful balance between the wing size, because the wing is the primary area where you would put the solar cells on. The solar cell area can also be on the horizontal tail, for example. The battery capacity should be big enough to collect the energy, but should not be oversized because they are so heavy. The aerodynamic performance must be sufficient, so cleanness of the configuration is important. And of course, weight, as always in any aeronautical vehicle and any space vehicle, is of utmost importance as well. So that's what the designer faced. And solar-powered aircraft have been flown as early as the 1980s, and you probably know all the history from Paul McGrady to more sophisticated airplanes, but they all flew either just during the day or on the spot, and a couple of 500 kilometers around. The biggest aircraft, the unmanned Helios, designed by NASA and flown by NASA, unfortunately had an accident, and it crashed over Hawaii due to gusty winds. And we were lucky that we had access to the accident report, because we learned before we started to build or make significant mistakes what we should look at. This is our first spar for the demonstrator vehicle, and it's being load tested here to 3.5 G, and you see the cross section of this spar is rectangular. It's not a circle as on the Helios. And the other thing we learned and observed very early was that we made an initial ground vibration test with the major structural elements of the vehicle. We didn't have any wings on it, but we had the main spar, we had the tails on it, the fuselage and the cockpit, and we could, using that basic data, generate an aeroelastic model of the aircraft, considering what it would be if we had everything ready to fly. So that was a very important step in the design. And here we see that the solar panels, how they were manufactured and put together, lots of connection. You better make sure every one is good and the current can go through. Here you see a top view of the wing with the main spar and all the ribs, and you see that the ribs are designed by conventional grid, like in the old days when we had wooden frames, or in the old days model aircraft as well. And then you see how one of these panels is attached to this structure. You see the main spar, you see some fairings there, though the solar panel could be attached, and two ribs would take up the loads, the aero loads from the solar panels, and introduce them into the wings. Each panel is fixed in the front and in the rear, and each one together is fixed, well, let's say with Scotch tape, so not to carry over bending loads or shear loads from one panel to the other. The electrical connection goes span-wise because the orientation of each cell is the important thing when you connect them electrically. So, the design characteristics of the aircraft is interesting because there's only one design point. The mission will be flown basically at the same lift coefficient all along, and it's not the best L over D, but it's the minimum rate of sink, because that determines how much energy you need to keep the aircraft in the air. There's no CG shift during the mission because the battery has the same weight if the battery is fully loaded or empty. It's a true all-electric aircraft. The max design altitude is 28,000 feet. We do have quite significant crosswind limits for takeoff and landing. We do not have a pressure cabin, which would have been an additional, quite a significant weight penalty. And we do not have a heating system. So much for the pilot. We'll see a little bit more later on. So this is what came out as the demonstrator aircraft. It had a wingspan equal to the Airbus A340. You see the blue areas are the one carrying solar panels. And contrary to the Airbus 340, we have one pilot in there, and that he's also the one and only passenger. Now we had to build up our own flight control center, the telemetry, all the software and the hardware as well. That was done, and we flew the aircraft in Payerne, which is a military base in Switzerland. And 2010, the first hop actually was in December 2009, but we really got off only 3 feet off the ground because we were not supposed to fly in Dübendorf, where the aircraft was designed and built. So we had to go to Payerne in order to actually fly the aircraft and get off the airfield. So in July, we made the major milestone, which is the demonstration that after 24 hours, we would have equal or more energy on board the aircraft than at the start. And that flight was very successful. So the program managers and the president and the chief executive decided, now let's build the record aircraft. And also because we knew already handling the aircraft on the ground and at different airports would be a challenge, we should start operational flights to gain the necessary experience. So the new requirements for the record aircraft were a new latitude, because we designed actually the demonstrator aircraft to fly in June, first flight in June for this 24-hour flight in June in Switzerland, in Payerne. But going around the world, we would have to start a little bit further down south in, let's say, the Arabic Emirates, United Arab Emirates, and we would start around March. And the other thing is that we realized that we would have to fly the aircraft for 5 to 7 days in order to actually cross the Pacific Ocean in particular. Also the Atlantic could be that long. We had to give the pilot safety equipment, food, drinks, a new reclinable seat with integrated toilet. We had to have a pilot health monitoring concept. And of course, he had to sleep once in a while. A stabilization system. It's not really what you might understand as an autopilot. We have somebody here who designed it. It's more a stabilization system with a monitoring on top of it. And of course, we had all the communication navigation systems in there for long-range flights. Here you see the aircraft in June 2011 over Paris, and we were able to fly it there as well. And we then did our first intercontinental flight. The continents were relatively close to each other, but nevertheless, we crossed the Atlantic there and the Mediterranean, and we went into hot climate and had also a new experience, because one day we flew backwards because the predicted weather and the predicted wind were considerably higher, so the aircraft flew backwards, actually, above the ground. All right, while these guys flew the aircraft to gain this operational experience, the design team experienced a major problem, because this main spar broke during the load test. Well, this is why you do load testing, to find out whether there's anything wrong. So we were not very happy about it, of course, but we were happy that we found the flaw during the test. But the other side of the coin was that finding out what was wrong, how to fix it, building a new spar, testing it again, putting all the ribs on and so forth, will take us quite a bit more money and will probably require us to delay the next phase by a year. So the program bosses had to make a decision: can we finance it? What can we do to bridge the time? And the decision was, let's cross America. So in 2000, while the guys at home, the engineers and the manufacturing guys, did actually work on fixing the problem, the other aircraft was flown across America from San Francisco to New York. And a few things happened there as well, and I'll try to tell you. One of the things, we were in a big airship hangar in NASA Ames, and you could hardly see the big aircraft there. But we know not everywhere we would find a hangar big enough to store the aircraft for a day or the time required to find a new weather window to go ahead to the next leg. So a portable hangar was developed. It can be blown up, and it has 3 segments, one for each wing, and one for the center fuselage and the rear. So this is by itself 10.5 ton to transport if you go around the world and want to have your hangar somewhere waiting for you. So the plan crossing America was to go from the Golden Gate Bridge, and you see the aircraft right here over the Golden Gate Bridge in San Francisco in the background, to the Statue of Liberty. Well, this was a pit stop in Cincinnati. We didn't have the hangar there. It was just the aircraft arrived late in the afternoon, was supposed to fly off the next morning. And what we saw here, the dew point was critical, and the whole wing and, of course, fuselage, all the areas were underwater from the dew that was setting down there. And you can see the guys shoving the drops to the rear. Unfortunately, the water drops were finding its way into the ailerons. We did not have enough drainage holes in there, so we had to get some syringes from hospitals and veterinarian or zoos to get the water out again there. Because if you fly up with water in the wing and you go up in altitude, you may have a freezing condition, not as cold as in here, but maybe more ice. Now here you see the aircraft south of New York, JFK, in a holding pattern, ready to be intercepted by a helicopter, and where he would fly to the Statue of Liberty. What you can't really see, you see two engines there on the left side wing, and you see what is in between these two engines. And here is a hole of something like 8 feet on the lower side of the wing. And you see the foil which has come loose from at the nose. The pilot couldn't see it. He couldn't feel it. The helicopter did immediate picture and it was immediately sent over to Switzerland. The engineers were called in the middle of the night to gather and investigate the situation and come up with the solution. Now, making a water landing here with this aircraft is like if you are in a bathtub and your wife is handing you over the hairdryer. So you cannot really do a water landing. You have to bail out and let the aircraft go wherever it goes. Now, the good thing was that the pilot had not realized any severe handling problems with the air, or not at all, that there was this big hole on the other side. So it was decided, land as quick as possible. But the bad thing was we couldn't fly around the Statue of Liberty, and that was for the sponsors and for the pictures and for the marketing would have been a big thing. So we did land, and the airport JFK was closed down for something like 25 minutes in order to avoid any engagement of aircraft vortices with this kind of vehicle. Now, during the design, we also had done a design scaling program, the same one that I have been working on at Make Air actually 50 years ago. I started June 1967 in St. Louis. And with this program, we could do a lot of studies. That is, we could analyze requirements, we could do trade-offs, we could design the parameter verification and variation. We could generate sensitivity matrix, and we discovered, for example, the weight growth factor of this vehicle is above 4 to 4.5, which is the largest I have seen on aircraft. The F-15 had something like less than 3. The Eurofighter had less than 2 because it had a fixed engine. But that was interesting to really see and investigate the characteristics of the aircraft and see the sensitivities. Now, this is a design window for this aircraft, and you see several interesting and some limiting lines in there. We certainly wanted to have payload, and the higher the payload is, the higher the weight is going to be. You plot it, we have weight versus wing area. So the payload is critical. And of course, the wingspan, we wanted to limit the wingspans because of all the aeroelastic characteristics which we might run into. And the other thing which is interesting, that we had the wing chord as a design critical item as well. And here you see why. If we want to transport the aircraft, let's say from Switzerland to the Emirates, we have to get it into a 747. And the wing better not have a bigger chord than the diagonal of that opening of the 747. So that was an unusual design constraint. Here you see the mass distribution of the vehicle with the top contributors, the wing and the wing structure, roughly 35%, the engine, the gondolas, the batteries, everything in there, electrical part, almost the same, 35, so that gives already 70%, and then the fuselage and payload, 25%, and horizontal stabilizer, vertical stabilizer, very minor contributors. Carbon fiber was a major element, or the major element, and we had to do quite a bit of investigation and develop new schemes to come up with very, very thin and very, very light material to meet our weight goals. And you can see 45% of the material is carbon fiber. As a matter of fact, I heard once from a British engineer in a presentation like this, you can easily say, well, this is the content of carbon fiber. Nobody would object. It's close enough from the sound to carbon fiber. Here you see the wing assembly at Dübendorf, and you see it's quite a big wing, and the upper side is already covered. The lower side will be then covered with a foil. And what you can see here, how many women do we have here? You can train your husband to really work with the iron at home if you let him work on aircraft. Now, fortunately, June 2014, we were able to do the first flight, and as you can see by the weather, we didn't have much time. We were under pressure to meet a schedule, so we flew at these weather conditions for the first flight, and it was successful. And here you can see Markus Schergel, from formerly DLR, the test pilot for this vehicle, and Bertrand Piccard on the left-hand side and André Borschberg on the right-hand side. You see how happy they were that this was all successful. Now, the major difference between the S1 and the S2 configurations you see here, and what is most visible, is that the outboard engines have been moved inboard. The reason being that if you go across an ocean for 5 days and one of the engine quits, you have quite a bit of yawing moment generated by that engine, and you would almost have to shut down the other engine as well, and that would be a critical condition. So we moved the outboard engines inboard. They could also run on overload for quite a significant time, and you could throttle the outboard engine on the other side, and you could continue to fly with 3 engines, and you could also use the energy stored in the failed engines as well, because they were close together. The dimensions of the aircraft was a little bit bigger, 2.5 tons, roughly 250 square meters of wing area. And you see here that we did one other change. The fuselage used to be rectangular for aircraft 1 and is triangular on this one, which gave us an additional area to put solar cells on them. And that was, of course, beneficial. Now, going around the world, you have a couple of challenges. One I mentioned already, the technical challenge, because all the system on board have to work 5 to 7 days. And there's no other manned aircraft which would fly 5 to 7 days around without refueling and stay in flyable condition. So we had to make sure that everything was right on the technical side. Equally critical and challenging was the weather prediction. Not only on the day where you wanted to take off, because you could always delay the takeoff, but you had to predict the weather along the route, 5 to 7 days, and also at the point where you want to land and at alternate conditions. Nonetheless, the pilot who's on board has to stay fit for 5 to 7 days and be capable to fly the aircraft. So his medical condition is also a critical item. And then what many people may not think about early on, you have to do quite a bit of negotiation with the countries that you want to overfly. For example, China, we had very small corridors. We could not go where the weather was good. We had to fly where they told us to in terms of altitude and routing. Air traffic control played a big role as well, in customs, because wherever we landed, we had quite a bit of spare parts along. We had our own kitchen, so we wouldn't suffer from any food disease in China, India, or wherever. And all of that had to be brought into a country and taken away. And everything needed to be checked by customs. So that were operational things which nobody thought very early on. Now here's some example of the weather forecast or weather considerations that we had to do. These are the tailwinds if you want to cross the United States, and you see the tailwinds are best in the northern area, and that's what, if you want to go fast, then you would go there. But of course, going over the Rockies and encountering all kinds of turbulence levels, you wouldn't rather go there. If you go look on the energy side, you immediately see the southern area takes longer time to fly, but the energy collection is much easier and much safer. We did make a real virtual flight in 2014 using our programs which simulate the engine, the aircraft and all its behavior in terms of performance, and we used actual weather data. So in 2014 we finished the flight around the world with 12 stops, and it took from February 1 to almost the end of July. So we had at least an idea, and we of course trained the mission control center people of what they have to look for and what might happen. Now this is the living room of the pilot. The green stuff in the rear is the oxygen bottles. The yellow stuff there is food. The blue one is the seat, the reclinable seat, within toilet installed. On the left-hand side you have the throttle and of course instruments up front. This is the master bedroom. And it is not as easy as one would think. The rule and the solution was that the pilot should rest every 2 hours for 20 minutes, and he could thereby maintain, let's say, a sufficient alertness to take over the controls. Now, Bertrand Piccard, you did this training and this sleeping rhythm by self-hypnosis. He is an expert in hypnosis. And Andre Borschberg did yoga training. Now, it's always good to have at least 2 pilots. I offered myself also to fly the aircraft with one slight change. I said, okay, I would like slightly change the pilot resting. I wanted to sleep every 20 minutes for 2 hours. And that's why they didn't took me. Now here you see the dressing room. The temperature in the cockpit ranges from -20 to +35. There is no heating except for the gloves and the shoe soles. They can be electrically heated, so you have to pull your zipper up and down and get the warm clothes on or off. Of course, we had survival training in the vertical tunnel to see how you control a jump from the aircraft. They jumped into the water, the test pilot and the pilots as well, the facility of a German Air Force, and they learned how to get rid of the parachute and get into the dinghy and all that, which was necessary. We have to admit when the end of 2014 came, we were not ready with all the flight testing in Switzerland. So we transported the aircraft January already to Abu Dhabi, and you see how here the fuselage is put into the 747. We started Mission Control Center in Monaco, and we had a sponsor who provided the facilities, very nice facility at a very nice location, as you can imagine. And he's the Prince of Monaco. We could then start actually flight testing in Abu Dhabi. And we had to do that in order to finish all the test requirements and clear the aircraft. And we had at that time a 72-hour simulation of each of the pilots in a simulator. A nice lady from the Nestle company would serve the dinner, and the pressure was not as bad and the temperature not as cold as in the real aircraft later on, but nevertheless the sleeping cycle could be trained and demonstrated. And we had safety training, virtual flight, ATC routing, everything was negotiated. And most important, we had the permit to fly from the Swiss certification office. They were also in Abu Dhabi and gave the final signature there, so we could start the flight. And this is the actual route around the world. By the way, there were some smart guys who wanted to talk to the FAI in Switzerland, who monitors and controls and issues the flight record in the aeronautic world. And they said, why don't we just go to the North Pole in June, take off, make 2 rounds, and then we have rounded the world. Well, even the Swiss authority, FAI, would not do that for their fellow countrymen. So we had to cover at least 35,000 nautical miles, 35,000 kilometers around the world at a reasonable latitude. Okay, here you can see how the portable hangar worked in stormy weather. It worked well. And here you see another important aspect of the program. In the middle is the boss of the medical team, and his name was also Boss. And they, the Hirslanden team, monitored the health of the pilots prior, during, and after the flight. These are the medical parameters which were monitored. General condition of the pilot, he was interviewed from the ground, personnel from the doctors. resting and sleeping times were recorded, food and liquid consumption, taking in and coming out, medication, for example, against thrombosis, the pulse rate, and a fitness test was done. And in particular, the oxygen of the blood was measured at the forehead, at the finger, and that was the only parameter which were constantly transferred to the Mission Control Center. Now, here came the shock we had in Mandalay. 3 weeks we were waiting to get a good weather window to continue, and then all of a sudden Andrei Borschbeck got ill and he was diagnosed with shingles. Some of you may know what it is. If it is not treated right away and in the right way, then it can be very painful and can take 1 or 2 years to really get rid of it. So the diagnosis was correct. He was flown to Switzerland, and Bertrand Piccard had 3 flights in a row, and Andrei came back after 10 days and was ready to fly. And the first specific flight was planned to take 6 to 7 days from Nanjing to Hawaii, and after 1.5 days the weather turned bad, and we had to make an unplanned stop in Nagoya, which was already mentioned. The aircraft was out on the tarmac. We had people hanging on to the aircraft before we could bring in our hangar, and it was wrapped in plastic foil, but that did not really help. We had some flaps which were on the trailing edge to reduce the loads of the ailerons in particular, and they were damaged and had to be repaired. And we had also found that some other things in the stabilization system should be repaired. That was done, and after another relatively large wait, we decided we'll have a maintenance flight. If the maintenance flight is good, then we'll continue to Hawaii. The actual maintenance flight was done. The engineers actually said, it isn't good, we have to return. But the 2 big bosses, one in the pilot and in the pilot seat, and the other at Mission Control Center, had a very difficult decision to make. And that is against the advice of the Safety Review Board to continue the flight to Hawaii or go back. And that would have meant that we would have probably needed another year. And so the decision was made to continue, and the engineers did support that flight. We did 2 unusual things. We climbed very fast during the maintenance flight, and when the decision was made to continue, we loaded the batteries 3 times as high a current as previously. And we had, up to that point, 1 26-hour flight with the aircraft 1, and 1.5 days or 40 hours going to Nagoya. So we did not have a long time, multi-day experience. And we were surprised what the batteries did. We were always in the design phase afraid that the batteries would get too cold and we may lose energy. The contrary in this particular case was that the batteries were became too hot during the very strong climb, and during the charge, very strong charge. And you see the battery temperature raised up to their limit. Fortunately, we did reach Hawaii in spite of this temperature issue with the batteries. And At arrival in Hawaii, the analysis of the batteries revealed that at the high altitude and the high temperature, low pressure, they had lost gas, and the chemical system was not good enough to say, okay, we'll just have them cool down and continue. So that cost us another 9 months to get that ready, but we had flown a 5-day mission, and the aircraft by then had, I guess, 8 official records by the FAI. Now here is something which one might also be interested in and is important. How much did the pilot sleep during these 5 days? How much did he rest? One of the issues was we could not really differentiate between rest and sleep. So both are added up, but the total resting time is, as you can see, between 4 and 5 hours per day. Not very attractive for somebody who likes to sleep. So it took us 9 months layover in Hawaii to manufacture, test, install new batteries, design, test, install battery cooling system, and also improve the stabilization system. And then we had to do some flight tests and obtained another permit to fly by the Swiss authorities. We finally arrived in San Francisco, crossed over to Hawaii, to New York. Finally, we're over the Statue of Liberty, and you see we had enough people on the ground and in the air to make nice pictures from that event. We also did make a nice landing in Hawaii, in New York. And here you see another thing which everybody is doing every so often. This is a selfie from the cockpit of the aircraft. You can see it's an unusual picture. The crossing from New York to Spain, Sevilla in Spain, was uneventful. It took only 3 days. And we had to wait there for another week or 10 days to continue to Cairo. And we saw the sunrise at the pyramids there, also some nice pictures, and finally arrived back in Abu Dhabi in July of last year, after some very interesting years, 12 years of work on the program. So we completed that flight without a single drop of fuel, and that is certainly a first for energy consumption of renewable energy. Now, the Solar Impulse team accomplished the innovative design, manufacture and testing of this manned aircraft, which can fly only with solar power and all-electric propulsion system many days and nights. And its capabilities have been proven by a successful circumnavigation of the world, including crossing of 2 oceans. The whole flight hours, 560 hours for that very flight. Now the Solar Impulse, that's I think important because many people who are not familiar with solar-powered aircraft and propulsion and comparing it to commercial flights, the Solar Impulse concept cannot be transferred to commercial flights as we have them today, because the energy which is collected from the sun is much too low to let us fly at current speed with the current comfort. But the message that this program is sending out is that we have technologies available right now to save energies and to provide new clean energy today, and we must use these energies and this approach to leave a world for the next generation as a clean environment So we have a good idea of that we did our job for the next generations. So that is basically the message, and here you see part of the team assembling around the aircraft, and as you can imagine, they are all very proud to have been able to participate in such a successful program. All right, that is the end, and I'm 8 minutes over time. So we have 3 more team members here, and if there are any questions, the difficult ones I will direct to them. And why don't you come on up and show your shirts as well?
And before we get to Q&A, it's my honor and my pleasure to present you with the Wright Brothers Medal. Shall we do that now?
I'm open to it. I mean, if you have such an offer, you cannot ignore it.
Exactly. So I was gonna get this out of the case and put it around your neck, if you don't mind. So why don't we stand here?
Okay.
That looks good on you. And also we have this certificate.
Thank you very much.
Sure.
Yeah. Okay. Thanks a lot. And what I didn't say at the very first part, I would like to thank AIAA and all the guys who are in AIAA for picking me and inviting me to give this lecture today. And so that will be a highlight in my professional life.
Excellent. So I think we're a little over time, so as the MC, I think I'll dispense with the Q&A given the time and the hour.
Okay.
Thank you very much, and thanks to the audience for your attention. And so one more round of applause.